All right, so in the last video, we proved this theorem. So it basically is uh, telling us how to find the order of a to the k given the order of a, and a consequence of this is the following. So in a finite cyclic group G, the order of an element divides the order of the group. In a finite cyclic group G, the order of an element divides the order of the group. And it's pretty easy to see. Let's say that, well, G is a cyclic group, so it is generated by, let's say, A, and let's say the order of A is n. So by this previous theorem, then every element of G would be some power of k, some power of A. So let's say a to the k. So every element of G looks like a to the k. And the order of a to the k by the previous theorem, right, it is the order of A divided by the GCD of k and order of A. And so from this equation, I see that the order of A is equal to the order of a to the k multiplied by the GCD of k and the order of A. Now, you see that then the order of A is divisible by the order of a to the k. So every element of G is some power of A to the k, and the order of G is the same as the order of A because A is a generator for G. So we see that the order of any element of G divides the order of G. Okay. Here is another consequence of the previous theorem. So here G is the group and A is an element of the group of order n. Then the subgroup generated by a to the I is the same as the subgroup generated by a to the j if and only if the GCD of n and I is the same as the GCD of n and j. Well, once we apply the previous theorem, it's easy to see why this is the case. So by the previous theorem, we know that the subgroup generated by a to the I is the same as the subgroup generated by the GCD of I and the order of A. And so also the subgroup generated by a to the j is the same as the subgroup generated by a to the GCD of n and j. Well, clearly these two are equal if and only if these two are equal. So clearly the subgroup generated by a to the I is equal to the subgroup generated by a to the j if and only if the subgroup generated by a to the GCD of ni is equal to the subgroup generated by a to the GCD of n and j. Well, then we know that then these two are equal if and only if the GCD of n and I is equal to the GCD of n and j. Another corollary is that, again, G is a group, A is an element of order n. The subgroup generated by a to the k is equal to the subgroup generated by A if and only if k is relatively prime to n. That is, the GCD of k and n is 1. Well, by the previous corollary, we know that the subgroup generated by a to the k is the same as the subgroup generated by A or a to the 1 if and only if the GCD of k and n is equal to the GCD of n and 1, but that's equal to 1. So we see that the subgroup generated by a to the k is equal to the subgroup generated by A if and only if the GCD of n and k is the same as 1, where n is the order of A. This is not part of the proof, but I want to make a remark here that if A is obviously a generator of the subgroup generated by A, and A to the K is also a generator of the subgroup generated by A if and only if the GCD of K and N is 1, that is K is relatively prime to N. A direct consequence of this corollary, that is, if I apply this corollary to the set of integers mod n, but now, you know, when we look at this corollary, we are assuming multiplicative notation, but nonetheless, it is also applicable to the case when we have additive notation for the group operation. So if I apply this corollary to Zn, then I get that an integer k in Zn is a generator of Zn if and only if k is relatively prime to the modulus n. Let's do an example. So if I look at Z50 star, Z50 star, you can check that it is a cyclic group of order 20. It's a multiplicative group, and 3 is one of the generators. So the question is, what are the other generators? Well, the order of 3, of course, then if 3 is a generator for this group, then the order of 3 must be 20 because that's the order of the group. And the other generators, by our previous theorem here, the other generators, remember the remark that I made here, the other generators would be powers of 3 where the exponents vary over the positive integers between 1 and 20 that are relatively prime to 20. Okay, so the other generators would be the powers of 3 where the exponents will be relatively prime to 20. So how many generators then we have for Z50 star? Well, there are phi of 20 generators for Z50 star because phi of 20 is the number of integers between 1 and 20 that are relatively prime to 20. And so basically you can write down the powers of 3 where, you know, so the other generators would be what? So 3 to the power 3 would be another generator because 3 is relatively prime to 20. 3 to the 7 would be another generator because 7 is relatively prime to 20, and so on. Okay, so I'm going to stop here. In the next video, we will be looking at the fundamental theorem of cyclic groups.